In this installment, we're going to look at forces in circles. And the key term we want to know is centripetal forces given by the variable Fc, force centripetal. An overview of where we are in the course, how this fits. We have mechanics, which is the subject of this course, kinematics, which is the description of motion. We have our dynamics, which is why things move the way they do, which is governed by two major laws, the law of conservation of momentum and the conservation of energy being the second. What mediates those two concepts are forces, and we have looked at a large number of forces, the last one being weight, and then we are considering geometric cases. And the first of those we already looked at was an inclined plane. In this case, we are going to be looking at circles. And so it turns out that any or all of these forces that we could look at can be applied to an inclined plane and or circles. And so the cases we're looking at now, the centripetal forces, are really just about one geometric application to a wide variety of forces. So let's look at this word centripetal in greater detail. Centripetal, there's a centra part, which comes from center, which probably needs no explanation. And petal is from the Latin petera, which means to seek. And we've seen that before. That is the reason we have P is mv. The momentum is petera, or to seek, seeking motion. In this case, centripetal then means center seeking. It is center seeking force. So a force directed toward the center. Our cast of characters in this case can be broken down into linear and circular versions of formulas and relationships we have. So we are very well familiar with Newton's second law, F net equals ma. Well, in a circular context, we can say the net force that's causing the acceleration is due to the mass times the centripetal acceleration. Centripetal acceleration. Now, as a reminder, the average velocity in the linear world is delta x over delta t. Now, how that applies on a circle, let's say we have an object that is here like so, and it is traveling at a constant speed. Well, this arc length, delta x, in the given delta t's, will be the same. So we could view this as an object traveling on a circular path. This might be us in outer space looking at an object traveling on the Earth. Now, to the traveler at that scale, they think they're traveling in a straight line. And the fact that the line is curved is not all that critical because the curvature is not really operating at the scale they're looking at things. But from our perspective, from an astronomical perspective, looking back on this, we could see that the delta x is actually on a curved line. But nonetheless, just like we could measure the distance on a road and divide it by the time, that gives us the average velocity. Well, now in a circular context, let's imagine now that we are looking at an entire revolution or path around. In this case, then, if we traveled the entire distance around, that would be the circumference. And the length of time that it takes to do that is called the period, capital T. Circumference and period. Now, circumference is given by the equation 2 pi r, and the t is t. So we could express average velocity as delta x over delta t, or as the circumference divided by the time, circumference being 2 pi r divided by the time, or the period in this case. So there's several expressions we have for the velocity. Now, getting back to this acceleration, which is defined as the average acceleration is the rate of change in velocity, delta v over delta t. Well, that's in a linear case. In a circular case, the centripetal acceleration, so previously this was the linear acceleration, the centripetal acceleration, meaning center pointing acceleration, is equal to v squared over r. And this is a complex derivation that would take a good solid 30 minutes or more to do. And it's not really necessary for us to derive that here in this course, but to know that it is true, we're going to do a different derivation about why the acceleration is why it is center pointing. So I am going to prove to you that it is center pointing. That when an object travels in a circle, in a circular path at constant velocity, that the change in velocity at any moment in time is toward the center. Now, given that then that we are just going to accept this, you're going to take it on faith, that that's true, but it's what you can find everywhere in every physics resource, is that centripetal acceleration is v squared over r. Well, v, we said, is 2 pi r over t. And when we put 2 pi r in over t for v and square it divided by r, we get 4 pi squared r over t squared. And I'll do that for you right here quickly on the side so you can see what that is. We have v squared, which is 2 pi r over capital T squared over r. So that then gives us 4 pi squared r squared over t squared. And that is times 1 over r. We then, of course, can see that this r cancels that squared, and we are left with 4 pi squared r over t squared. And that's our centripetal acceleration. Now, taking the last step, bringing us home to Newton's second law with the F net equals ma, the F net is m delta v over delta t, which is the acceleration, the linear acceleration. In the centripetal world, that force causing things to accelerate toward the center is called a centripetal force. And it is equal to mac. So the mass times the centripetal acceleration, which is v squared over r, gives us m times 4 pi squared r over t squared. For perspective, the formula we're given from the AP reference table is this alone. Simply this. But if we know that the average velocity is 2 pi r over t, we can arrive at, and F equals ma, we can arrive at Fc equals that. So keep in mind, we need to know this, or be able to derive this, to end up with this type of expression that we could see later. So this is an introduction to forces in circles. Those forces are called centripetal forces, center pointing, which means they're directed toward the center. And since the force is toward the center, it is a vector toward the center, then the centripetal acceleration is toward the center. Force toward the center, acceleration toward the center. And we have clear linear and circular analogs or applications of those, keeping in mind that we will need to come up with our own expressions for Fc. In our next installment, we're going to pursue centripetal forces in greater detail.